Paul did his PhD at MIT under Silvio Macaulay. Has been at Berkeley for a few years now as an NSF postdoc. Sort of has worked in a broad range of areas, doing sort of a number of things, some of them very eclectic, some of them more conventional, from algorithms to complexity to algorithmic game theory to cryptography. And that's going to be reflected in his talk today, which is on the challenge of data efficiency. So.
Okay. Good afternoon. Thanks for the introduction. Thanks for inviting me, and thanks for being here. So the challenge of data efficiency, vignettes from statistics and evolution. So computing is entering a new era, a era of big data. And to give two kind of thought-provoking examples, so on the left we have the Large Hadron Collider, the kind of emblematic science experiment of our time, which is collecting new data from the universe at a rate of about 1 gigabyte per second, I'm told. On the right, we have some victory shot from IBM's Watson computer system winning Jeopardy recently, using what is, essentially the scanned contents of 1 million books in its databanks. We're finally reaching an era where there's a data explosion, where we can bring to bear a huge amount of data on almost any problem. And we're just starting to get a sense of what we can do with this. This is kind of a watershed event, I want to argue, and kind of an analogy with the computational explosion from the 1940s. So before the 40s, a computer was essentially something like this, a kind of typewriter with essentially no memory, where you could do calculations, but then suddenly in the 1940s, computers became these things with non-trivial amounts of processing power and memory, and this changed computing. So this somehow immediately inspired a new algorithmic style of thinking. With in the 40s, merge sort, linear programming, many other algorithms, without which it's almost hard to imagine computer science. So somehow, before the 1940s, no one had asked the question, how fast can you sort a list of numbers? And it wasn't that computation was new in any sense. So people had been computing things for hundreds of years. So ever since maybe Newton, people were numerically computing differential equations. Hundreds of digits of pi were known. But somehow the presence of real physical computers instigated this watershed event of algorithmic development. So the question is, what will be the fruits of the data explosion? So in this talk, I'm going to give you two kind of vignettes from opposite ends of the spectrum. So on the left, a very concrete problem from statistics that's sort of been known about for hundreds of years, for at least 100 years. We kind of thought we knew the answer for basically 100 years. And I'm going to show you how to do just a tiny improvement to what everyone thought was possible, which will actually kind of resolve this problem to within constant factors. And this is joint work with my brother Gregory. And in the other half of my talk, I want to maybe just inspire you by what is, in some sense, the best big data story I know. So evolution. So somehow, as a result of the data inherent in billions of interacting creatures, evolution has worked its magic, and we are the result of big data. So this is a phenomenon. Evolution is a big data phenomenon that I think deserves a lot of further study in our terms. And of course, I'm not going to tell you the secret of life in this talk, but merely tell you some early positive results hinting at what further work can be done, and just kind of cheerleading for this area. So we'll start on the left with statistics. So the distinct elements problem. This is a classic problem. It's stated as follows. So you have a table with n elements, and you can examine as many elements as you like. The question is, after you've examined some bunch of elements, can you estimate the number of distinct elements in the whole table, even amongst those you haven't seen? So you want to approximate this to within, say, plus or minus epsilon times n. So approximate it to within, n over 10 or something like that. Okay, so how many entries do we need to do this? So suppose we take, say, 1/10 of the entries. Is this enough to figure out, to estimate the number of distinct elements from the 90% of the data that we haven't seen? So what might we do to estimate the number of total distinct elements? So for example, we could estimate 1/10 of it, and then just report the number of distinct elements we've seen. So in this example, we've seen apples, oranges, bananas, and a pineapple. So we could say, okay, I've seen 4 kinds of fruit, so I bet there are 4 kinds of fruit here. But you know, this will often be an underestimate. For example, there could be some obscure fruit hidden away in corners, a kiwi, a dragon fruit, and just seeing a tiny fraction of the data, we won't see them, and we won't report them. Okay, so by contrast, we could try examine n over 10 things and report 10 times the number of things we've seen. So this, you know, has to be an upper bound, but of course it could overestimate things. You could try something more complicated. So examine n over 10 of the items and report the number of distinct things that you've seen multiple times, plus 10 times the number of things that you've only seen once, as kind of an estimate for perhaps the number of rare events that. But this doesn't work, but this is sort of along the flavor of stuff that's been tried before. Okay, so this is a motivating question for us. So more generally, how can we estimate properties of distributions? And again, I'm going to focus on the large alphabet case, when it's a distribution over many items, because this is the big data case. And statisticians have done a pretty good job for the kind of classic small data case. What I'm going to tell you about is an improvement which only shows up in the big data case. Okay, so rephrasing the distinct elements problem in this framework, you could phrase it as follows. Estimate the support size of a distribution, D, each of whose elements occurs with probability that's either 1 over n, 2 over n, 3 over n, etc. So this corresponds to the process of, in the table on the previous slide, just picking at random an element. And how many times do you have to pick an element at random before you have enough data to estimate to within plus or minus epsilon how many distinct elements there are? So generalizing this, so estimate some property of the distribution which is guaranteed to have support at most n. So we're going to parameterize everything in terms of n. As you can see from the previous slide about distinct elements, n is kind of the fundamental thing here. You expect the answer to be roughly n. So we're parameterizing things by n and asking, can we beat n? So just to write down some notation here, not that this notation will be relevant. I'm writing this down just for the purpose of pointing out that there are many different problems that you can put under this framework. But for the rest of this talk, in fact, all this notation will not matter at all. They'll all be under the same framework and analyzable by the same theorems, but I just want to present to you a little bit of the variety of what you can do here. So if p sub I is the probability of seeing element I, then the distinct elements problem is just the sum over the domain of the truth value of is p of I greater than 0. The entropy of the distribution is the sum of the negative of p sub I times log of p sub I. So this is a very standard information theory measure. Or if you have, say, 2 distributions. So the pink distribution, d prime, is a different distribution on the same elements, where p prime sub I is the probability of hitting element I in the second distribution. You can ask things like, what's the L1 distance between the 2 distributions? So sum up over each element the difference between the probability of seeing it in the 2 distributions. So these are kind of 3 paradigmatic problems of this area. And for each of them, we ask, how many samples do we need to estimate this quantity to within plus or minus epsilon? Okay? So just to give 2 kind of motivating examples, so curiously credited to R.A. Fisher and Alan Turing, arguably the founders of, the grandfather of modern computing and statistics. So 2 stories which both happened in England in the 40s, but in very different contexts. So to just tell the Fisher story, so this naturalist, Corbett, spent 2 years in the Malayan jungle collecting butterflies. And these are his raw data. So this thing here indicates that there were 120 species of butterfly that were so rare that he only saw 1 example of each species. Meanwhile, there were about 75 species that he saw 2 examples of in his entire 2-year period, 45 species of butterfly that he caught 3 examples of. So he mailed this data back in some letter to R.A. Fisher, who was safely in England, and asked, is it worth me to stay more years in this jungle? If I spend another 2 years in this horrible jungle, how many new species of butterfly will I discover? And in some sense, it sounds like an impossible question for statistics to answer. He's asking about butterfly species that no one has ever seen ever, and asking, if I spend 2 more years observing butterflies, how many new things will I discover? As it turns out, there's a remarkably simple answer, which R.A. Fisher mailed back, which is the following. Given this data here, this 120, the 75, 45, just take an alternating sum of it. So take 120 minus 75 plus 45, et cetera. And this will, in fact, reveal a very accurate estimate of how many butterflies you'll discover if you spend 2 more years in the jungle. Kind of expressed in a formula, if you just call these things H1, H2 just for histogram. This is the formula. As part of the German war effort, on the other hand, Turing was dealing with a sort of similar kind of problem of phrased in butterfly language. What's the probability that if I catch 1 more butterfly, it'll be of a new species? And the good Turing estimator is just expressed as a formula this. The first histogram entry divided by the total number of samples you've seen. So these are remarkably effective estimators, and this is kind of the first hints that there is that you can in fact predict huge amounts about unobserved data. Okay, so who cares about these problems? So just to generically wave hands here. So I was invited to this workshop on information theory and statistics for large alphabets at the Banff Center in Canada. And beyond the kind of obvious interest represented here in information theory and statistics, we heard about problems and applications from a variety of other areas: databases, electrical engineering, neuroscience, the internet, of course, biological engineering, compressed sensing, physics. So there's a large community of people for whom collecting data is expensive, and you want to figure out what's the most efficient use you can get of the data you have. Okay, so the main result. What can I tell you about how to approximate these properties of large alphabets? So the answer is n over log n. Of course, time's a constant, which depends on the problem. And of course, a dependence on epsilon and the error that you're allowed, which depends on the problem. But for the purpose of this talk, I just want to focus on the commonality here, the n over log n, which is the same for all of the problems I've mentioned. So one way of looking at this is you need only 1 over log n fraction of the data you thought you did. Or another way of talking about this is, given a certain amount of data, you can actually simulate having log times more data than you actually drew. So this is a kind of general principle here. Okay, so prior work. So on the algorithmic side, the naive estimator for entropy is just, if you see some data, take the entropy of what you've observed, report it. And there was a lot of work, I guess, in the 50s and 60s on so the Miller-Maddow corrected estimator, the jackknifed estimator, all things which converge in some sense better for the easier cases. In 2002, the first kind of papers which really try to analyze this from a computer science perspective looked at multiplicative approximations to entropy. Recently, there have been a number of streaming papers trying to analyze how much you can do with limited memory. But all of these fall under the big O of n rubric. So none of them broke this linear barrier for how many samples you need to actually estimate entropy itself. Though Paninsky in 2003, a neuroscientist, published an existence proof that sublinear time is possible. So non-constructive existence proof, and this is kind of hints. The lower bound side, which I won't really talk about because, as you can perhaps see from the numbers here, things get very complicated very fast. So there's a kind of obvious birthday paradox lower bound of square root of n, so you can't do anything with less than square root of n samples. And depending upon whether you're doing entropy or distinct elements, some lower bounds of n to the 2/3 and and n over 2 to the little o of root log n log n. So things get very complicated. In my thesis a few years ago, I proved a lower bound of n over 2 to the square root log n. But still, there's a large gap between this and n. And that's what I'm going to resolve today. Breaking the linear barrier. So just as an unofficial mantra, so linear algorithms deal with data as it comes. This is very useful. Superlinear algorithms cannot. Sublinear algorithms somehow don't even need to see the data. Sublinear algorithms somehow can do magic. So this is a sharp threshold at linear in terms of what you should think about the algorithm. So just to give a illustrative example, so you have some website like Amazon.com, and a bunch of users interact with your website. So if typical users interact with your website, say once a month, question is how many months of data do you need to estimate statistics of these users? So the traditional answer is that, well, if typical users interact with your website about once a month, you need at least a month to see these users. And today, I'm going to tell you how you can actually do this in 1 over log n months. What's n? N is the number of users. So if it's something like Amazon.com, you have 100 million users, and this is actually perhaps a significant savings. So what might you want to know about your users? Well, beyond just how many there are, you might want to know some more delicate information, sort of like the entropy of the balance between the rare users and the frequent users. Or maybe you have 2 websites, and you want to compare how users use the 2 websites, draw some statistics about which users use one and not the other. So again, this is a framework which applies to many problems. As in many problems in our field, the solution becomes clear, at least in retrospect, if you draw the data in the right way. So on this slide, I'm going to tell you how to draw the data in a way that I'm going to call histograms, which will make a lot of things rather intuitive. So just to recall what we're trying to do. So we have a probability distribution, which is unknown, from which we get some certain number of samples. And the question is, given these samples, to what degree can we recover information about the original distribution? So, OK, let's draw a distribution. Suppose we have a distribution which is uniform on 1,000 elements. I'm going to draw it like this. So there's a bar at the x-coordinate 1 over 1,000 to indicate that everything is happening with elements that have probability mass 1 over 1,000. And the bar goes up to height 1,000, indicating that there are 1,000 elements like this. OK? The only change I'm going to make is if it turns out that, for example, we'll take 10,000 samples from this distribution, I'm going to rescale the x-axis by 10,000, sort of to indicate that each element of the domain of the distribution we expect to see 10 times. OK? So what happens if we actually draw samples from this distribution? We get something like this. This is drawn the same way as the butterflies were on my first slide, indicating that, for example, there are maybe 120 items that were seen 8 times. OK? So if we draw samples from the distribution, we get something like this. The expectation is a binomial curve. And I want to draw your attention to 2 things here. So what we're trying to get at is the transformation from red to green, the transformation from the actual distribution to what we see of the distribution. So this transformation does 2 things. It spreads it out, and then there's some noise added. And I want to say that this is sort of like what happens in a digital camera. If you take a photograph of a scene, 2 things happen. First of all, the scene becomes blurrier because of defects in the lens, for example. And also, it's noisy because of sampling issues in the electronics. So if the original image is, say, this delta function here, then the image you observe when you actually take a picture might be some kind of noisy, blurred-out version like this, if each of these things here is the location of a sensor on your digital camera. OK? So this is noise being spreading out in the x direction, and blur meaning uncertainty in the y direction. The second thing I want to point out is that the expected value of this transform, the expected value, the stars, is in fact a linear function of what we started with. linear in the following sense. So if we start out with this delta, with the uniform distribution on 1,000 elements, we get this curve. If we start out with, if we start out with the uniform distribution on 3,000 elements, namely each element is now going to be seen roughly 3.333 times if we take 10,000 samples, then the expected samples, then samples are like this, the expectation is like this. But furthermore, if we take some linear combination of these two things, so denoted by this histogram, where some of the elements have probability 1,000th, some of the elements have probability 1 over 3,000. Then if we take samples from this, it'll be something like some linear combination of the two expectations I just drew. So this is in fact a linear transformation. So the transformation from the true distribution to what we observe, from red to green, is a blur with noise, and it's a linear transformation. So the question is, given this linear transformation, this noisy linear transformation, how do we recover information about the original distribution? So we're going to use one of our favorite sledgehammers, linear programming. Okay? So we've got a bunch of linear constraints with noise. So we can encode this as linear programming, as a linear program in the following way. So the linear program is the following. Find distributions whose expected histograms, whose expected behavior is close to what we observed. So this is not an exact transformation. It's a noisy transformation. So there will be inequalities here instead of equalities. And that's why it's linear programming. So write down this linear transformation, whatever it happens to be, make it into inequalities by accounting for the noise, and then this will define a feasible region where anything inside this feasible region is, in some sense, a distribution where the observed data could have come from. Given this feasible region, what do? Take any point in it, and if you want to find the entropy, take the entropy of this point you have. If you want to find the number of distinct elements, just count the support size of this arbitrary point in the feasible region. For any other property, it's a completely black box method. So step 1 is solve a linear program, find any element in the feasible region. Step 2 is the actual property of your data that you care about. Just plug it in a black box manner. Okay, so how well are we doing? How well can we do? So to analyze this, I want to just keep the analogy of earlier of taking a digital photo, and say that it's very much like the image processing task, that you start out with an ideal image on the left, and then what you observe is a blurry and noisy version of that. And the question is, to what degree can you recover the original image? Okay? So this is a standard image processing task. So under kind of reasonable standard assumptions, so specifically for those of you who care about this, if you take a Gaussian blur and I'm measuring blur as the square of the radius of the blur, namely like the variance of the blur, the result is the following. If you want to de-blur by a factor of c, namely decrease the amount of blurring by c, this will amplify the noise by e to the c. And this is a general phenomenon. Phrased slightly differently, just taking logs of both sides here. So if you have d noise headroom, as in if your camera sensor is good enough that you can afford to amplify the noise by a factor of d, this means that you're allowed to do image processing that de-blurs by a factor of log d. Okay, so what does this actually work out to for the example that we have here? So the amount of blurring for this sampling process turns out is just proportional to 1 over the number of samples. Meanwhile, the noise is roughly 1 over the square root of the number of samples. In the same way that if I take n coin flips and see how many times I get heads, it won't be exactly 50%, but it'll be 50% plus or minus 1 over square root of n. So the noise that you get from just flipping coins or from sampling is 1 over square root of n. Okay? So since blur is proportional to the number of samples, we get this curious effect that if we de-blur by c, this essentially means we're emulating taking c times more samples. Meanwhile, because our noise is 1 over square root of n, and we can afford to have it as high as epsilon, whatever error we're allowing ourselves, we've got roughly square root of n noise headroom. We can afford to amplify the noise by up to roughly square root of n. So together these imply that we can afford to deblur by the logarithm of square root of n, i.e., one can emulate taking a half log n more samples than we actually have access to. Okay? So this is the intuition for why we can do log factor better than everyone thought we could. And this is also the intuition for why you can't do any better than this. That you only have square root of n noise headroom. So no matter what you do, you can never deblur by more than this half log n. Actually proving this is much more work than I have time for today. So the lower bound comes from several directions. So the deblurring lemma is related to what I just talked about in the last slide, but for Poisson distributions instead of Gaussians. There's an explicit construction of a lower bound counterexample, but the big heavy lifting comes from proving a new multivariate central limit theorem. And all these contain a lot of components which I would love to talk about if anyone has questions afterwards, but which I'd rather skip in favor of telling you an interesting story about evolution. We're going to switch gears here to the other side of big data, the side where I'm going to prove a relatively small thing, but perhaps convince you that there's a lot more to be done. Okay, so evolvability. So in each cell of your body, encoded in your DNA and enforced by your DNA are equations like this, expressing that the concentration of chemical Z is going to be 0.41 times the concentration of chemical X plus 0.89 times the concentration of chemical Y. These are encoded in the DNA, and they're enforced by the DNA in the chemical way that cells operate. The conjunction of these kind of relations are often called protein networks, and you get these complicated graphs that look kind of like the internet. And they lead us to a very real concrete question of, first of all, how did your DNA arrive at coming up with the right relation here? Relations that work together in a harmonious way so that they lead to survival and not to something ridiculous. Furthermore, because life is full of surprises, when the conditions of life change, how do the parameters in these expressions update themselves in response to the new conditions of life? So this is a computational question. It needs an explanation. And that's what I'm going to tell you about today. So the field of evolvability is kind of the conjunction of concerns from two areas, evolution and pack learning theory. So the connection with machine learning would be enough to justify giving this talk in front of a computer science audience. But I want to claim much more. I want to claim that evolution, the secret of life, is fundamentally a computational phenomenon and not a biological phenomenon. And hopefully, if you're with me until the end of this talk, you'll be half convinced of that. Okay, so how is evolution like learning? So learning theory kind of takes place in the following framework. You have a distribution of examples, and you're trying to train a function which is going to classify these examples correctly. For example, you have a distribution of images of animals, and you're trying to train a function to correctly classify these images. So you get a picture in, and your function responds with, I think it's a dog, and then you evaluate the performance. Is this a satisfactory labeling of this image? So meanwhile, in nature, nature presents your DNA with examples. For example, nature, an actual cat leaps at you, and your DNA encodes some response to this. It's chemically enforced by your DNA. For example, you start sweating. And nature is constantly evaluating our performance. Do we survive and reproduce? To give a kind of more concrete example, so nature, for example, gives you an environment where the concentration of chemicals X and Y in this environment is 0.73 and 0.49 respectively. What concentration of enzyme Z does your DNA produce? And evolution is the game of your DNA changing over the course of many generations so that, in principle, it responds appropriately to the challenges that nature offers it. Okay? So in both circumstances, pack learning and evolution, it's really important that this work for essentially any distribution. It's not as though the images that we want to classify are the uniform distribution over all potential arrangements of pixels. It's some very strange distribution, whatever the distribution of images of dogs and cats actually is. It's not uniform, it's something strange. And similarly for nature, any explanation of evolution that we come up with, if it doesn't handle a huge variety of conditions of nature, we've sort of failed at our task. Okay? So evolution is like learning. But, okay, it's not exactly like learning. It's a severe limitation of learning in that when you're doing machine learning, you're presented these examples, you classify them right or you classify them wrong, you get some feedback, and then you can choose how to update your function, your classifier, for the next round of things. In nature, though, your DNA doesn't process life examples and figure out how to update itself. At least in Darwinian evolution, it doesn't. In Darwinian evolution, all that happens is your DNA shows up on Earth, either it survives or it doesn't. So Darwinian evolution is like learning, but with survival or death as the only feedback to the next generation. You're not allowed to do arbitrary processing on your inputs. Okay? Okay, so there's been a lot of previous work on the subject, all of it in the Boolean model in analogy with pack learning theory. So in the Boolean model, nature has a distribution over binary vectors, 0, 1 to the n, and each creature responds with either 0 or 1. So there's been a variety of work. I want to draw your attention to, I guess, two aspects of this. So the main kind of impossibility result here, which distinguishes evolution from learning, is that evolution cannot ever learn the class of parity functions. So it is by reduction to this statistical query model of, I guess, Michael Kearns from about 20 years ago, that if you only have if you can only ask statistical questions of the data, if you can't see individual examples of it, then there's no way to learn a parity function. To learn parity, you essentially need to have access to your data and solve, and just write down the data and solve the linear equations, and then you can learn a parity function. If you only can ask questions like, okay, here's my DNA, do I survive or do I fail? Do I have a good guess of the parity function or don't I? Then it's impossible to learn parity. So this is kind of something which draws a big distinction between the power of machine learning and the weaker power of this evolvability model. On the algorithms side, so all these papers present algorithms, and the trade-off you see here is between what I could call power and naturalness. That if you prove, if you throw some really heavy tools at the problem, you'll be able to prove some powerful result about what evolvability can do. But on the other hand, these powerful tools won't look like it's something that evolution could actually be using. So there's a trade-off here that we'll see more in the rest of the talk. Okay, so today, in contrast to the Boolean model in which all previous work has been done, I want to introduce real evolvability, where everything is over real numbers instead of Boolean numbers. So, okay, let's tell you the components of the model. So nature has a distribution D over real vectors in Rn. Nature also has, implicitly, of course, some best function, some best response to each of the possible conditions that nature gives you. Some function from, say, length n vectors to length m vectors. Meanwhile, each creature's DNA encodes some hypothesis function, h, also from length n vectors to length m vectors. And the game is played as follows. For each creature, take a bunch of samples from nature's distribution, and then rate the creature by comparing how the creature responds to this implicit best performance that is kind of defined by nature. I don't mean explicitly defined by nature. I don't mean you can look around in the universe and find the description for the perfect creature. I just mean that nature is constantly evaluating us. So implicitly, there's some function which has a best performance. Okay. So for the moment, comparing our performance with how the best creature would perform, I'm just going to use the L2 metric. So just take the difference and square it. But there's many more variants that are possible, and I'll talk about those a bit more later. Okay, then what happens? Survival of the fittest. So just to make a simplifying abstraction here, the details turn out not to matter very much. The best creature, C, survives. So you rate all the creatures, you stochastically rate all the creatures, and the best creature survives. Then there's a mutation algorithm, which in terms of the DNA of creature C, determines the DNA of its children. And the kind of result that we're looking for is the following. A class of functions f is evolvable if there exists M, a way of mutating, a mutation algorithm, such that whatever distribution D nature may have in mind, whatever best function f nature may have in mind, this evolution process here will yield a near-optimal hypothesis in reasonable time with high probability. This is the kind of result that we seek. And the main result I'm going to tell you about is that fixed-degree polynomials are evolvable here. So low-degree polynomials, this is a very natural class to look at because low-degree polynomials can approximate a lot of other things. And in particular, they include these kind of linear functions which, for example, protein networks are often described in terms of.
Good question.
Yeah.
So you don't have any crossover here. So how is evolution in your sense different from just pre-research?
Okay, so it's actually possible to model crossover in this model. So adding crossover over to this model provably doesn't increase the power of this model. One way to see that is that this thing that I've been calling a creature, C, if instead of encoding the DNA of a single creature, if it encodes the DNA of every creature alive at a certain segment of at a certain time slice, then the mutation algorithm can do crossover itself. So the mutation algorithm is an arbitrary function in terms of the DNA currently. So if your DNA encodes every creature that's alive, you can just have the algorithm cross over. So crossover, crossover doesn't actually add to the power of this. Again, the main purpose of this talk isn't to say that this is a model for how evolution works, but just that this is something which is a model of how evolution could work. This shows that you can do a lot even with these limited abilities. There's, of course, many very promising open questions about how you can try and do more. And I'll hint at those at the end, okay? Let me tell you about the simplest possible algorithm for mutating DNA. So recall again that we've got a polynomial. We're trying to evolve some fixed degree polynomial, which is described in terms of some coefficients, a coefficient for 1, x, x squared, et cetera, but in some higher dimensional space. So we need to figure out how to change the coefficients p into some mutated coefficients p prime. So this algorithm will be parameterized by two bounds. The details don't really matter, but think of them as being something that's smaller than anything you're likely to encounter and larger than anything you're likely to encounter, little b and big B, 10 to the minus 100, 10 to the 100. And we'll do the following, which perhaps you might believe is about as simple as you can possibly expect anything to be and still work. So pick a random number between little b and big B. Pick it in some fair way, like pick a random power of 2 between little b and big B. And then step 2, modify p by radius r in a random direction. So pick a random vector that's got length r that we just chose, add it to p. Okay? This is the simplest possible thing that has any chance of working. And so I call this just wide-scale random noise to emphasize that you've got a lot of different sizes you can pick, but other than this, it's just random noise, okay? And the result is that wide-scale random noise involves all polynomials over all distributions under the L2 scoring, okay? L2 scoring, again, is where we evaluate our performance by comparing how you do to the optimal thing by just subtracting and squaring, okay? So this is a simple algorithm, and simple means that evolution could work in this sort of way. Simple also means that although I've proven this one particular theorem, there's nothing about this particular algorithm that's targeted at this theorem. So because it's so simple, one could imagine proving much more general theorems. I don't know how to do this, but I imagine that this wide-scale random noise algorithm might work much more generally because it is so simple. Okay, so how does one analyze this? So just to remind you of what our target is. So fitness is the expected value over the following. So draw examples from life's distribution, figure out what life's ideal answer, what life's ideal response to this is, compare it to your response, and square it, okay? Again, more generally, one can consider some arbitrary loss function that does some arbitrary, computation between how you respond to the best response. But for the moment, let's just compare them and square it. So when does wide-scale random noise lead with high probability to optimal fitness for every distribution? One kind of sufficient condition, a proof technique, is to show that with non-negligible probability, this mutation algorithm will yield some fitness improvement of at least some threshold. And therefore, if you have enough children, at least one of your children will pick the right thing, and progress will always occur. So to give a concrete example, suppose we're talking about quadratic polynomials from R3 to R, just to write something down. So the data points that life presents us, the challenges that life gives us, are these three-dimensional vectors, so x, y, z. And meanwhile, so you evaluate a degree 3 polynomial by just, it's parameterized by 10 coefficients, h1 to h10, that you just multiply by these, this constant vector of 1 x, y, z, x, y, x, z, y, z, x squared, y squared, z squared. And again, this is a constant vector because for the moment we're saying that we're fixing the example that life gives you, okay? So how you perform is, how you respond to life's challenge is a linear function of your coefficients. Okay, so if we compare this with the ideal response and square it, this is now a convex quadratic function. This is just for one example d from life's distribution. In reality, we care about an arbitrary distribution of these things. But if you take a mixture of different convex quadratic functions, if you take a sum of convex quadratic functions, it'll be convex and quadratic. So overall, fitness is this convex quadratic function of what's in your DNA. Okay, so how do we analyze this? So quadratic functions we can kind of draw as ovals in high-dimensional space. So this is a level set. This is a set of points that have some certain fitness. And the center of this oval is the best fitness function. And each of the concentric ovals are other level sets of this fitness function with correspondingly worse fitness as you get further from the center. So the ideal function, f, is at the center. Meanwhile, we have some hypothesis that's on some other level set far away. And what do we do? Well, we do wide-scale random noise. So we pick a random radius, and then pick a point at this radius. How well does this work? Well, if we pick a small enough radius, then with probably a half, we're going to move inwards. With probably a half, we'll move outwards. So if we pick a radius which is big enough that it's still roughly of the size of how far we have to go to reach the center, then with probably, so if we pick a small enough radius, we'll go towards the center with probably a half. If we pick a big radius, we might actually make significant progress. If you pick just the right radius, then say maybe you'll still go towards the center with probability a third. And the point about this wide-scale random noise process is that even if you have no idea of what radius to pick, if you're just picking a random power of 2, then with logarithmic probability, you're going to pick the right radius. And then with probability 1/3, or with probability close to a half, you'll end up going towards the center instead of away from the center. So overall, with roughly 1 over logarithmic probability, you'll make consistent progress here. And that's how you prove it. Just to draw your attention to this thing. So our proof technique here was that with reasonable probability, mutation will yield some reasonable fitness improvement. What can you do more generally? So to what degree, what's the relationship between evolvability and optimization in general? So what I presented to you was kind of a hill climbing or like valley descent algorithm. And to what degree is evolution the same thing as this? To what degree can we implement more powerful variants of optimization algorithms in this framework? Can you take your favorite optimization algorithm and re-encode it as an algorithm in this evolvability framework? So there are kind of 3 obvious difficulties. The first one is just that the stochastic nature of everything, that you cannot ever exactly realize your fitness, but nature presents you examples and then grades you on how you perform, so you can only approximately figure out your fitness at any time. And of course, if you're trying to implement your favorite optimization algorithm in this framework, you need to somehow use the DNA as your program memory. You need to somehow read in this approximate fitness into your DNA. So these 2 issues I won't talk about. A recent paper by Vitaly Feldman showed how to do this in the Boolean model. And instead, all that leaves us is this barrier that we can't do any optimization algorithm we want because we can only ever approximately figure out the function value, the fitness value of where we are at the moment. But this is the only barrier, as it turns out. So the result theorem, and this is kind of the second main theorem of this part of the talk, is that evolvability is the same thing as weak optimization, where weak optimization is just exactly the class of things you can do when you only can ever approximately figure out the function value. Our favorite weak optimization algorithm, our favorite optimization algorithm that only requires approximate access to the fitness value, the ellipsoid algorithm. So any convex function you can weakly optimize. So any convex function, given only approximate access to it, you can approximately optimize. So if the conjunction of the function class, the distribution, and the loss function yield a convex function, evolvability will work. And specifically, this implies that the class of polynomials is evolvable for all distributions and for all convex loss functions. Instead of just for the quadratic loss function, for any convex loss function, the ellipsoid algorithm will optimize it. Okay, so further directions. So there's a gap between what we can prove via natural evolvability algorithms, such as this wide-scale random noise, versus very artificial things, like this reduction to the ellipsoid algorithm that we can never imagine DNA actually implementing an ellipsoid algorithm reduction. So natural algorithms seem to behave somewhat like simulated annealing in that they always accept improvements and they sometimes accept slight declines. So the question of kind of, can we learn about simulated annealing via studying evolvability or vice versa? And can we analyze, for example, simulated annealing or the wide-scale random noise algorithm to show that it in fact works beyond the case that we've been able to prove so far? Okay. I just want to end with a comment about evolvability, what I've been telling you about, versus evolution, the kind of more general phenomenon. Have I succeeded at this talk? Well, in some sense, I still haven't addressed anything like the fundamental problem of how do you explain the eye or any of the other really amazing results of evolution. On the other hand, I want to say that this is maybe small steps in the right direction. So if learning nice multivariate functions were not possible in a reasonable evolution model, evolution would be in trouble. So it's reassuring that we can actually concretely show some results in these directions, even though, of course, the bigger problems remain. So evolvability, in some sense, is adapting to a fixed environment, which is in some sense analogous to a small time slice of evolution. If you take a small enough time slice of the world, then the conditions of the world may be fixed enough that you can model them as just a probability distribution. As the conditions of the world change, then it's not a distribution, but it's something that changes. And this notion of modeling a small time slice versus evolution being a big time thing is in some sense the divide between microevolution and macroevolution that you hear about in political circles, for example, where the microevolution side is the plausible, easy side, and the macroevolution side is the implausible sounding, impressive side. And the results today are very much in the micro side. So I just wanted to end with a little cartoon. So biologists, have gotten a number of very impressive stories where you take some animal, you take some very close look at it, see its DNA, sequence it, and then if you're very lucky, you can even catch it mutating. And you can come up with some story that explains this mutation, explains what it does. And this is microevolution. You've caught one little thing changing. In some sense, I want to say that this is analogous to taking some impressive piece of computer hardware, looking at it really closely and saying, okay, at a really fine level, if I look at this one tiny portion of what it's doing, register 2 becomes register 1 plus 7. And if you zoom into this level of detail, the whole thing becomes trivial. The whole thing becomes boring. I want to say that it's almost the same thing on the other side, that to abstract from this micro level out to the macro level, this is an algorithmic problem. It's not a biological one. Starting with these trivial parts and assembling to a functionally impressive device is what we as computer scientists do. So this is our problem. Evolution is our problem to solve, and I want to encourage you guys to think about it. Thanks.
All right, thanks. Any questions for Paul? Pedro?
Can you relate what you've done here to the literature on theory of genetic algorithms?
Yes, so to some extent, this algorithm I presented is not a very impressive algorithm. I mean, the fact that it optimizes convex quadratic functions, this is not an impressive, groundbreaking, optimization result. So if you were trying to write an optimization algorithm tomorrow, I would not suggest that you use these results. The point here is more just to try and model this small portion of evolution which was hitherto unexplained and show that, in fact, it can be done in a sort of plausible way.
Okay, any more questions? All right, so if you have questions, Paul's around until the end of the day tomorrow. Let's thank him again.